Right now, as you're listening to this, a killing is taking place inside your home. Not a metaphorical one, a biochemical one. On every doorknob, every faucet handle, every coin in your pocket, an invisible massacre is unfolding. And the killer is a reddish metal you use every single day without giving it a second thought. You know that smell. Sharp, cold, metallic. You've known it since childhood. And you're probably convinced you know exactly what it is. You don't. Because metals don't actually smell. At all. That's not poetic exaggeration. It's physics. At room temperature, metal atoms don't evaporate into the air. They can't reach the receptors in your nose because there's nothing there to reach them. A metallic smell is, technically speaking, impossible. What you just smelled wasn't the metal. It was your own skin. The moment you touched copper, its ions began reacting with the oils on the surface of your hand, breaking them apart into volatile organic compounds. One of those compounds is called Oct-1N31. That's the molecule responsible for what we describe as the smell of iron, copper, or blood. What you're smelling is the aftermath of a chemical attack on yourself. It happens in a fraction of a second, without your knowledge, without your permission. Welcome to the story of Element 29. The only metal that can build civilizations and kill bacteria more effectively than some modern antibiotics. A metal that saves lives and can destroy minds. A metal that has served humanity for 9,000 years while guarding a scientific mystery that some of the world's brightest physicists still can't fully explain. A metal we're desperately running short of. And one whose scarcity has already helped bring entire civilizations to their knees. Tonight, somewhere in Chicago, thieves will cut copper lines out of residential air conditioning units. In Detroit, abandoned buildings are already being stripped of their wiring. In Las Vegas, workers loading spools of copper cable onto a truck might look like contractors, but not all of them are. And somewhere in Houston, someone will risk their life trying to steal live power lines. Some won't survive the attempt. According to FBI estimates, copper theft costs the United States roughly $1 billion every year. This isn't petty crime. It's a nationwide epidemic. Hospitals lose power. Traffic systems fail. Entire neighborhoods go dark. People are willing to gamble their lives for a reddish metal. Why? Because right now, a war is being fought over copper. Not a metaphorical war. A real one. A $1 trillion struggle that may determine the future of modern civilization. A single electric vehicle contains roughly 180 pounds of copper, about 4 times as much as a conventional gasoline-powered car. A 3-megawatt wind turbine requires between 3 and 5 tons. Every data center powering today's artificial intelligence is wrapped in miles of copper wiring. Without it, even the most advanced processors on Earth would overheat and fail within minutes. The world wants a green future. A green future requires a red metal. And we don't have enough of it. What's rarely discussed is that this isn't the first copper crisis. We've been here before. More than 3,000 years ago, a shortage of copper helped trigger one of the greatest collapses in human history. Within a single generation, entire civilizations vanished. The Hittites, the Mycenaeans, the kingdom of Ugarit, the Minoan world. Egypt survived. Barely. We'll come back to that, because what happened then may be a warning for us now. But first, we need to answer a much stranger question. Where did copper come from in the first place? Because the answer begins long before Earth existed. And it will completely change the way you look at the metal in your pocket. Not a single atom of copper was created on Earth. Not one. Every gram of copper in your home's wiring, your plumbing, your laptop, your phone, or the coin sitting in your pocket is older than the sun itself. It's the ash of a dead star. To understand why, we need to spend a few minutes thinking like nuclear physicists. Every star is a giant fusion reactor. Deep inside its core, immense pressure forces atomic nuclei together. Those nuclei fuse into heavier elements, releasing enormous amounts of energy in the process. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. Then silicon, magnesium, sulfur. Each stage burns faster than the one before it. Our sun has been quietly turning hydrogen into helium for about 4.6 billion years. It has roughly another 5 billion to go. But massive stars live very different lives. Stars 8, 10, or 20 times heavier than the sun burn through their fuel at a terrifying pace. And eventually, they reach a wall. That wall is iron. Iron is the end of the line. The ultimate nuclear dead end. Up to iron, fusion releases energy. Beyond iron, fusion consumes it. Trying to build heavier elements from iron is like pushing a boulder uphill forever. The moment a star begins producing significant amounts of iron in its core, its fate is sealed. The countdown to death has begun. Copper is element 29. Far beyond that limit. An ordinary star can never make it. To create copper, you need something far more violent than a star's death. You need two dead stars to collide. On the 17th of August 2017, scientists operating the LIGO observatories detected a signal unlike anything humanity had ever observed before. One detector sat in Louisiana, the other in Washington state. Both recorded the same disturbance. Space-time itself had begun to ripple. The source was located about 130 million light-years away, in a galaxy called NGC 4993. There, two neutron stars had finally reached the end of a cosmic dance that had lasted millions of years. A neutron star is what remains after a massive star explodes as a supernova. Imagine compressing more mass than our Sun into an object roughly the size of Manhattan. Matter becomes so dense that a single teaspoon would weigh around 6 billion tons. That's roughly the weight of Mount Everest squeezed into the volume of a spoon. For millions of years, the two neutron stars spiraled closer together. orbit by orbit, second by second, until finally they collided. Physicists call the resulting explosion a kilonova, and explosion hardly does it justice. In less than a second, the event released more energy than our Sun will produce during its entire 10 billion-year lifetime. Temperatures surged into the hundreds of billions of degrees. Matter was compressed to such extreme densities that atomic nuclei began capturing neutrons faster than they could decay. This process, known as the R process, or rapid neutron capture process, allowed matter to leapfrog through the periodic table, creating heavier and heavier elements in a matter of moments. Across the world, telescopes swung toward the source. Just 1.7 seconds after the gravitational wave signal arrived, astronomers detected a burst of gamma rays, then visible light, then the glowing aftermath expanding into space. Spectroscopic analysis revealed something extraordinary. The debris cloud contained newly forged heavy elements: gold, platinum, uranium, and copper. For the first time in human history, we weren't merely theorizing about where these elements came from. We were watching them being born, in real time. 2 dead stars, each more massive than the Sunday, compressed to the size of a city, colliding 130 million light-years away. And inside that cosmic catastrophe, copper came into existence. Your copper, the copper in your pocket, the copper in the wires carrying this signal to you right now. Billions of years ago, somewhere in or near our galaxy, a similar collision took place. A cloud of debris rich in newly formed elements expanded into space. Over time, it mixed with vast clouds of gas and dust drifting through the Milky Way. Then, about 4.6 billion years ago, one of those clouds began to collapse under its own gravity. The result was our solar system, the Sunday, the planets, and eventually Earth. As the young Earth formed, gravity sorted its ingredients. The heaviest elements sank toward the center: iron, nickel, gold. Much of it disappeared into the planet's core, more than 1,800 miles beneath our feet. Locked away forever. Copper behaved differently. Geochemists call it a semi-siderophile element. Part of it followed iron downward. Part of it stayed behind. Some remained trapped within Earth's mantle. Some became concentrated in the crust, locked inside minerals such as chalcopyrite, malachite, and azurite. Malachite glows bright green. Azurite shines a deep, vivid blue. Colors impossible to miss against gray stone and brown earth. Thousands of years later, those colors caught the attention of our ancestors. And that's how humanity first found copper. Not because it was useful, not because it was rare, not because anyone understood chemistry, but because it was beautiful. Among all the elements in the periodic table, copper may be unique. Its relationship with humanity didn't begin with technology. It began with curiosity, with color, with beauty, and with someone, somewhere, stopping to pick up a strange green stone and wondering what secrets were hidden inside it. Most of us learned about the Copper Age as a footnote, a brief transition between the Stone Age and the Bronze Age. A few crude tools, primitive people, a shiny rock. Turn the page. Move on to the real civilizations. That version of history is wildly misleading. Because copper didn't simply improve human technology, it changed the way humans thought. On the 19th of September 1991, two German hikers were crossing a glacier in the Alps near the border of Austria and Italy. More than 10,500 feet above sea level, they noticed something sticking out of the ice. At first, it looked like a recent tragedy. A mountaineer, maybe someone who had died a few decades earlier. Rescuers were called. The body was recovered. Then came the radiocarbon dating results. The man wasn't decades old. He was over 5,300 years old. Today we know him as Ötzi the Iceman. He was carrying a collection of surprisingly sophisticated equipment, clothing made from animal hides, a quiver filled with arrows, a flint knife, and a copper axe. That axe would force archaeologists to rethink what they knew about prehistoric Europe. When researchers analyzed the blade, they discovered something astonishing. The copper was approximately 99.7% pure. Think about that for a moment. Modern industrial methods for routinely producing copper of that purity didn't emerge until the 19th century, with the development of electrolytic refining. Yet here was a man living around 3,300 BC carrying a tool whose metallurgy rivaled some early industrial products. But the bigger surprise came later. Scientists performed isotope analysis on the metal and traced its origin. The copper had come from ore mined in what is now Tuscany, hundreds of miles away from where Ötzi died. That single discovery changed everything, because it revealed something hidden behind the artifact itself. A system. 5,000 years ago, people were already mining ore in one region, smelting it in another, shaping it into finished tools somewhere else, and transporting those products across mountain ranges. That requires specialization, trade, logistics, supply chains. This wasn't primitive survival. It was an economy. And Ötzi wasn't an exception. In present-day Serbia, at an archaeological site called BOTTLENECK, researchers uncovered evidence of copper smelting dating back roughly 7,000 years. That's the 5th millennium BC. Nearly 2,000 years before the first Egyptian pyramid. People in the Balkans were building furnaces capable of reaching and sustaining temperatures above 1,984 degrees Fahrenheit, the melting point of copper. They knew how to process ore, how to control airflow, how to separate metal from slag, how to pass specialized knowledge from one generation to the next. This wasn't experimentation. It was engineering. Meanwhile, on the other side of the Atlantic, indigenous peoples around Lake Superior were mining native copper as early as 9,000 years ago. Long before the wheel, long before writing, long before cities. On Michigan's Keweenaw Peninsula, miners were already extracting metal from the earth. What emerged there may have been North America's first large-scale mining industry. A technological revolution so ancient that most people have never heard of it. And here's why copper mattered so much. Stone tools are limited by geology. You work with what nature gives you. A flake of flint, a shard of obsidian. The material dictates the shape. Copper changed that relationship completely. For the first time, humans could imagine a tool and then create it. The material no longer controlled the design. The human mind did. That shift sounds subtle. It wasn't. It was one of the most important cognitive breakthroughs in human history. Matter had become programmable. The physical world could now be shaped to fit an idea, not the other way around. And then someone made an even bigger discovery. We don't know who. We don't know exactly where. But at some point, somebody added tin to molten copper. About 10%. The result was bronze. And bronze changed everything. It was dramatically harder than pure copper. It held an edge. It resisted deformation. It could be cast into complex shapes. The difference between copper and bronze wasn't incremental. It was transformational. Almost overnight, the world divided into two groups. Those who had bronze, and those who didn't. The first built kingdoms. The second paid tribute to them. Even the word copper tells part of this story. The Latin word cuprum comes from Cyprium ace, metal from Cyprus. The island of Cyprus was rich in copper ore, so rich that its deposits became one of the strategic resources of the ancient Mediterranean. Egyptians wanted it. The Hittites wanted it. The Mycenaeans wanted it. The Phoenicians wanted it. Cyprus wasn't a vacation destination. It was an arsenal. But bronze required more than copper. It required tin. And that's where the story becomes surprisingly modern. Because tin was rare. Very rare. The Mediterranean world had almost none of it. To obtain tin, traders had to reach far beyond the boundaries of their own civilizations. Some supplies came from Cornwall in southwestern Britain. Others traveled from Central Asia. Some may have originated near present-day Afghanistan. The result was one of the first truly international supply chains in history. Thousands of miles of trade routes connected distant regions by land and sea. Cargo ships, merchant caravans, storage depots, security forces. More than 3,000 years ago, an interconnected global economy already existed. And then it broke. Around 1200 BC, the Bronze Age world began to collapse. Historians still debate exactly why. Perhaps it was climate change, years of devastating drought, perhaps earthquakes, perhaps internal rebellions, perhaps invasions by the mysterious sea peoples. Most likely, it was all of them at once. A cascading systems failure. The details remain uncertain. The outcome does not. The Hittite Empire vanished completely. Mycenaean Greece entered a dark age that lasted centuries. Writing disappeared. Cities emptied. Population levels collapsed. The wealthy trading kingdom of Ugarit was reduced to rubble and never rebuilt. The Minoan world disappeared from history. 5 major civilizations gone within a single generation. Historian Eric Klein famously described this period as 1177 BC, the year civilization collapsed. Imagine waking up tomorrow to discover that the United States, China, the European Union, India, and Japan had all ceased functioning. Not gradually. Not over centuries. Within 30 years. That's the scale of what happened. And at the center of that collapse sat 2 metals, copper and tin. The nervous system of the Bronze Age world. When the supply lines carrying those materials were severed, the system seized up. The body of civilization became paralyzed. The lesson is uncomfortable. When a society becomes dependent on a critical resource, scarcity doesn't merely slow progress. It can trigger collapse. Fast. 3,200 years later, we're building a remarkably similar dependency. Only this time, the critical resource isn't bronze. It's copper. Copper for power grids. Copper for electric motors. Copper for data centers. Copper for the digital nervous system of modern civilization. Welcome to Bronze Age 2. And we're betting our future on the same metal all over again. Paris. The city is drowning in cholera. Thousands are dead. Hospitals are overwhelmed. Doctors are helpless. No one understands what's happening. The germ theory of disease doesn't exist yet. Louis Pasteur is still a child. Robert Koch hasn't even been born. The word bacteria means nothing to medicine. And yet one French physician begins noticing something strange. His name is Victor Burke. The pattern seems impossible. Workers in copper foundries aren't getting sick. Neither are jewelers, metal engravers, mint workers, casters. People who spend their days handling copper appear unusually resistant to cholera. Most doctors would have dismissed it as coincidence. Burke didn't. He spent years gathering data. He examined records from 3 separate cholera outbreaks, 1,832, 1,849, and 1,854. Workshop by workshop, factory by factory, street by street. And the numbers kept pointing in the same direction. People who worked with copper became sick far less often than everyone else. The difference wasn't subtle. It was dramatic. Burke presented his findings to the French Academy of Sciences. The audience listened politely. Then the world forgot about them. For nearly 150 years. Not because Burke was wrong, because he was too early. The bacterium responsible for cholera wouldn't be identified until 1883. The scientific tools needed to explain what Burke observed simply didn't exist. So his discovery sat on a shelf, waiting until the 21st century, until molecular biology finally caught up. One of the scientists who helped bring the mystery back into the spotlight was Professor Bill Keevil at the University of Southampton. And what researchers discovered was astonishing. Because copper isn't merely toxic to bacteria, it's a biological executioner. Imagine a bacterium landing on a copper doorknob. Let's say it's Staphylococcus aureus. The attack begins instantly. Copper ions interact with thiol groups found in proteins embedded within the bacterial cell membrane. In plain English, copper targets sulfur-containing structures that the cell depends on to stay alive. The membrane begins to fail. Its integrity breaks down. Ions rush across barriers that are supposed to remain sealed. The cell starts leaking. But that's only the first stage. Copper then triggers a chain of chemical reactions that generate highly reactive oxygen species, free radicals, molecular shrapnel. These radicals tear through the bacterium's DNA, creating damage faster than the cell can repair it. Genetic information is destroyed. Replication becomes impossible. The organism loses the ability to survive and dies. Now consider MRSA, methicillin-resistant Staphylococcus aureus, one of the most feared antibiotic-resistant pathogens in modern medicine, the kind that spreads through hospitals, the kind that shrugs off drugs designed to kill it, the kind responsible for thousands of deaths every year in the United States. On stainless steel, MRSA can survive for days, sometimes weeks. On copper, dead in about 90 minutes. Think about that. A piece of metal can accomplish something that challenges entire pharmaceutical industries. No electricity, no drugs, no intervention. Just chemistry. In November 2008, the U.S. Environmental Protection Agency officially registered copper alloys as antimicrobial materials. For the first time in history, a solid surface was legally recognized as a tool for fighting disease. Not a medicine, not a disinfectant, a metal. Clinical studies produced equally striking results. In one hospital trial, replacing commonly touched surfaces with copper reduced healthcare-associated infections by more than 50%. No new antibiotics. No revolutionary technology. Just a different material on bed rails, door handles, and workstations. Then came COVID-19. In March 2020, researchers from the National Institutes of Health published a study in the New England Journal of Medicine examining how long SARS-CoV-2 remained viable on various surfaces. On plastic, up to 72 hours. On stainless steel, up to 48 hours. On cardboard, up to 24 hours. On copper, about 4 hours. Copper was destroying the virus dramatically faster than steel. While the world fought the pandemic with masks, distancing, disinfectants, and lockdowns, one material quietly kept doing what it had done for thousands of years: killing microbes. No batteries required. No software updates. No patents. And maybe that's part of the reason nobody talks about it very much. Because you can't patent copper. But copper isn't humanity's friend. It's an ally. And allies can become dangerous. Because the same chemistry that makes copper essential also makes it potentially deadly. Consider Wilson disease, a rare genetic disorder caused by mutations in a gene known as ATP7B. Under normal circumstances, the liver regulates excess copper and removes what the body doesn't need. People with Wilson disease lose that ability. Copper begins accumulating inside the body. At first, the damage appears in the liver. Inflammation, scarring, eventually cirrhosis. But then something worse happens. The metal crosses the blood-brain barrier and reaches the brain. The symptoms read like the slow collapse of a personality. Hand tremors, loss of coordination, difficulty speaking, anxiety, mood instability, sudden aggression, hallucinations, cognitive decline. As copper builds up inside neural tissue, the mind itself begins to unravel. And physicians often notice one particularly striking clue: a thin ring around the iris, gold-green, almost metallic, known as Kayser-Fleischer rings. Copper announcing its presence from inside the body, visible through the eyes. The average adult needs only about 2 milligrams of copper per day. That's all. An amount so small it's easy to overlook. But the margin for error is surprisingly narrow. Too little copper. The immune system weakens. Red blood cell production suffers. The nervous system begins to malfunction. Too much, and the consequences can be catastrophic. Evolution didn't choose the safest element. It chose one of the most effective. Then balanced us on a razor's edge. Which raises an intriguing question. What if evolution had chosen differently? What if iron wasn't the only solution? Because here on Earth, another answer already exists. Octopuses, squid, cuttlefish. Their blood is blue, not bluish. Blue. Because instead of relying on hemoglobin, they use a completely different oxygen-carrying protein called hemocyanin. At the center of hemoglobin sits iron. At the center of hemocyanin sit 2 copper atoms. When oxygen binds to those copper atoms, the molecule turns a brilliant blue. And in some environments, it actually works better than our system. Cold water, low oxygen, the deep ocean. Conditions where iron-based blood struggles. Thousands of feet below the surface, Entire ecosystems run on copper chemistry rather than iron chemistry. It's a reminder that biology didn't have to look the way it does. Life could have taken a different path. And in some corners of the planet, it did. But if there's one creature that truly reveals copper's importance, it's not an octopus. It's a horseshoe crab. Horseshoe crabs have existed for roughly 450 million years. They survived every major mass extinction in Earth's history, including the Permian extinction, the worst biological catastrophe our planet has ever experienced. They're older than dinosaurs, older than trees, older than most groups of insects alive today. And their blue blood contains specialized cells called amoebocytes. When those cells encounter bacterial endotoxins, they clot almost instantly. That reaction has become one of modern medicine's most valuable safety tools. Every vaccine, every injectable drug, every implanted medical device manufactured in the United States must be tested for dangerous bacterial contamination. And for decades, that testing has relied on horseshoe crab blood. A single liter can be worth tens of thousands of dollars. Think about the irony. A creature older than the dinosaurs, running on copper-based blood, helping protect human health in the 21st century. The same metal that kills bacteria on a doorknob is helping keep vaccines safe. And somehow, that's still not the strangest thing about copper. Because the deeper we look into this element, the weirder it becomes. Copper is the second best electrical conductor found in nature. Only silver performs better. There is an international benchmark known as the International Annealed Copper Standard, or IACS. When engineers created it in the early 20th century, they needed a reference point. So they chose pure annealed copper. Copper became the standard. 100% conductivity. The benchmark against which everything else would be measured. Then they tested silver. The result came back at roughly 106%. Silver was actually better than the standard itself. 6% better. Which raises an obvious question. If silver conducts electricity more efficiently, why isn't modern civilization built on silver? The answer is simple. Cost. Silver performs slightly better. Copper is vastly cheaper and available in quantities large enough to wire an entire planet. Civilizations are rarely built on perfection. They're built on compromise. Copper happens to be one of the best compromises nature ever produced. And then there's gold. Humanity spent thousands of years worshipping it. Empires rose and fell over it. Wars were fought for it. Even today, gold remains locked away in places like Fort Knox as a symbol of wealth and stability. Yet as an electrical conductor, it's mediocre. Only about 70% as conductive as copper. Gold's real advantage is something else. It doesn't corrode. It doesn't oxidize. It doesn't tarnish. That's why it's used in electronics. Not because it's the best conductor, because it's the most reliable. The digital world wasn't built on gold. It was built on copper. Not because nothing better exists, because nothing better exists at scale. The world currently produces about 22 million metric tons of copper every year. That sounds like an enormous amount. It isn't. According to projections from analysts at S&P Global, global demand could reach 35 to 40 million tons annually by 2035. That leaves a potential shortfall of roughly 10 million tons every year. 10 million tons. A gap so large there is no obvious way to fill it. And that's where the uncomfortable reality begins. We keep talking about the transition to a green future as though it's simply a matter of political will. Build more electric vehicles. Install more solar panels. Construct more wind farms. Expand the grid. Electrify everything. The problem is that all of those solutions depend on the same material. Copper. Lots of it. An electric vehicle contains roughly 4 times more copper than a conventional gasoline-powered car. A modern wind turbine requires tons of it. Solar farms require miles of copper cable. Power grids require copper. Charging stations require copper. Data centers require copper. Artificial intelligence requires copper. Every path to the future seems to pass through the same bottleneck. And that bottleneck is getting narrower. This isn't politics. It's arithmetic. So why not replace it? Engineers have been asking that question for decades. The obvious alternative is aluminum. It's cheaper, it's lighter, and it's abundant. But it comes with serious trade-offs. Aluminum conducts electricity less efficiently. Its connections degrade more easily over time. And under certain conditions, it can create dangerous fire hazards. Many Americans learned that lesson the hard way. During the 1960s and 1970s, aluminum wiring became common in residential construction. Years later, thousands of electrical failures and house fires were linked to those systems. Today, aluminum wiring remains a major concern during home inspections and real estate transactions across the United States. What about graphene? Scientists love graphene, and for good reason. It's extraordinarily strong, remarkably conductive, potentially revolutionary. There's only one problem. Nobody has figured out how to manufacture it at the scale required to replace global copper demand. Not even close. And fiber optics? They've already replaced copper in many telecommunication systems. Light carries information far more efficiently than electricity. But fiber can't power a motor. It can't run a transformer. It can't energize an entire city. The fundamental problem remains. Modern civilization doesn't simply use copper. It depends on it. Copper is no longer just a commodity. It's infrastructure. It's the circulatory system of the industrial world. And right now, demand is beginning to outpace supply. The largest producer of copper today is Chile. Roughly a quarter of the world's supply comes from there. including output from the massive Escondida mine, the largest copper mine on Earth. Peru follows close behind. Then comes the Democratic Republic of the Congo. And that's where this story takes a darker turn. Because metals don't emerge from the ground by magic. Every ton of copper comes from somewhere, and somebody pays the price. In parts of the Democratic Republic of the Congo, reports from international organizations and human rights groups have documented conditions involving forced labor, dangerous working environments, and child labor associated with mining operations. Armed groups have fought for control of resource-rich regions for decades. Profits from minerals have helped fuel conflicts that have claimed millions of lives since the 1990s. Which means the supply chain doesn't end when you buy a product. Your smartphone, your electric vehicle, your solar panels. Their story stretches far beyond the showroom, far beyond the factory, all the way back to the mine. 3,000 years have passed since the Bronze Age collapse, yet the underlying formula hasn't changed. Whoever controls critical resources shapes the rules. Everyone else adapts, or struggles, or fights. And now, as demand continues to rise, humanity is considering options that once sounded like science fiction. One of them is deep-sea mining. Far below the ocean's surface, along mid-ocean ridges, hydrothermal vents continuously pump mineral-rich fluids into the water. These environments create massive sulfide deposits containing copper, zinc, gold, and other valuable metals. Several companies and governments have already begun exploring technologies capable of harvesting those resources. On paper, the idea is seductive. A vast untapped reserve of critical minerals waiting on the seafloor. But the environmental risks are enormous. Hydrothermal vent ecosystems are among the most unusual habitats on Earth. Many species living there exist nowhere else. Some haven't even been formally described by science. Mining operations could destroy these environments before we fully understand them. Sediment plumes might spread for miles. Toxic materials could be released into surrounding waters. Entire ecosystems could be altered permanently. Which leaves us facing an uncomfortable paradox. Copper is essential for reducing carbon emissions. Yet obtaining more copper can damage the very planet we're trying to protect. It's like treating a disease with a medicine that harms the patient. There is one piece of good news. Copper is almost infinitely recyclable. Unlike many materials, it can be melted down and reused over and over again without losing its essential properties. The copper recovered today is just as useful as the copper mined thousands of years ago. Roughly 30% of global copper demand is already supplied through recycling. Among industrial metals, that's one of the best recycling rates on Earth. If recycling rates increased dramatically, pressure on mining operations could be reduced. But even that isn't enough. Because demand is growing faster than we can recover old material. The math remains stubborn. The gap continues to widen. And for the first time in generations, humanity is confronting a possibility it hasn't faced since the Bronze Age. What happens when the metal your civilization depends on becomes the metal you can't get enough of? Because copper isn't merely powering the future, it may be limiting it. And that brings us to the final irony of this story. For all the urgency surrounding copper today, the metal itself couldn't care less. Long after we're gone, copper will still be here. Look at the Statue of Liberty. For nearly 140 years, she has stood in New York Harbor, facing the Atlantic. A symbol of freedom, a symbol of America, a symbol of permanence. But here's something most people don't realize. The Statue of Liberty is made of copper. Her outer skin is only about 3/32 of an inch thick, thinner than 2 pennies stacked together. When France presented the statue to the United States in 1886, it didn't look anything like it does today. It wasn't green. It was a warm, reddish-brown, the color of a brand-new penny. Over the next few decades, that color slowly disappeared. The copper turned green. Most people assume that's damage, corrosion, decay, evidence that time is winning. But the truth is exactly the opposite. That green layer is called patina, and patina is one of the reasons copper survives for centuries. As copper reacts with air, moisture, and carbon dioxide, it forms a thin protective coating on its surface. That coating seals the metal beneath it. It blocks oxygen. It blocks water. It slows further corrosion to a crawl. In other words, copper protects itself by allowing part of itself to die. It builds armor from its own destruction. Concrete eventually crumbles. Steel rusts. Glass shatters. Plastic degrades under sunlight. But copper endures, not unchanged, but intact. Archaeologists routinely recover copper artifacts that are 6, 7, even 8,000 years old. The surface may be altered. The color may have changed. Yet the object remains recognizable. Its shape survives. Its history survives. Its maker's fingerprints, metaphorically speaking, survive. And that's where this story becomes unexpectedly philosophical. Because copper may outlive everything we've built. Geologists who study the Anthropocene, the proposed geological epoch defined by human activity, often ask an unusual question. What evidence of our civilization will remain millions of years from now? The answer is surprisingly little. 10 million years from today, there will be no cities, no highways, no skyscrapers, no airports, no nations, no monuments. Tectonic forces will grind them down. Erosion will erase them. Groundwater will dissolve them. Sediment will bury them. Given enough time, even the most impressive structures humanity has ever built will disappear. The Empire State Building will vanish. The Hoover Dam will vanish. Every stadium, every bridge, every tower, gone. But something may remain. A thin chemical fingerprint. A faint green signature embedded within layers of rock. An unusual concentration of copper spread across the planet. Because every wire, every pipe, every motor, every transformer, every data center, every electric vehicle, every coin, every piece of copper humanity has extracted from the earth will eventually be broken down, recycled by geology, and incorporated into future rock formations. Millions of years from now, an intelligent species examining Earth's strata might notice something strange. A sudden spike in copper. A geological anomaly. A signal. Evidence that something unusual happened here. Something mined enormous quantities of a metal forged in the collision of neutron stars. Something stretched it across continents, wove it into vast electrical networks, used it to carry voices, music, images, knowledge, thought itself, and then disappeared. We like to think we're the masters of copper, that we mine it, refine it, shape it, control it. But on a geological timescale, the relationship looks very different. Copper was here billions of years before us. It will be here billions of years after us. We are merely a brief episode in its history. A bright flash between two immensities. For 9,000 years, we've built civilization around this metal. A skeleton of copper wrapped in concrete, steel, and glass. A planetary nervous system carrying the collective thoughts of billions of people. Every message, every phone call, every search query, every song streamed across the internet, every word you're hearing right now. All of it depends, in one way or another, on copper. The metal born in the death of stars. And one day, that system will fall silent. The last power line will go dark. The last transformer will cool. The last motor will stop turning. The last electron will drift through the last copper wire. And when that happens, almost everything we built will fade away. Almost everything. What remains may be nothing more than a green stain in stone. A thin line in the geological record. A quiet trace left behind by a species that briefly learned how to command the ashes of dead stars. Not marble, not granite, not gold. Copper. Element 29. Star ash that became civilization. and for one fleeting geological moment, worked for us.